examples in which classical mechanisms that we already know, such as reinforcement learning, can be applied in a quantum scenario, and how quantum neural networks can be also included into the equation. And now we are really looking forward to have an insight about it's okay? An insight about this is the kind of impact that can be created also by the quantum computing community. I couldn't think of a few people more suited for that than Artur. Please.
Thanks a lot for the invitation. Hi everyone, I'm Artur. I come from the Barcelona Supercomputing Center, which is a very classical computing center up to now, or up to very recently. I'm also a founder of Qilimanjaro. I'm involved in the Master of Quantum Technologies in Barcelona, which is also coordinated by John. I'm also teaching in the postgraduate course at UPC. So there is an interesting community in Barcelona, happening already for many years. I would say the BSc is probably the last member of this nice community. There are a lot of things happening, and I think these kind of events are very important. Like we get connections, and I really appreciate the invitation. So I didn't know about the audience, so I would like to explain two things. One is a very general picture of what we do at the BSc, because we are not very well known, honestly. And the other is a very technical part, very short, about one of the key different points that we can bring to this discussion. Okay, about quantum technology. The discussion on supercomputing centers about quantum technologies is becoming very relevant, and it's very recent as well. So for many years, quantum computing happened only on physics department, and supercomputing centers didn't care about that at all. But this changed dramatically a few years ago, and the main reason was funding. There was funding coming from supercomputing centers into quantum technology, and then everybody got very interested in it. Okay? So what we have at BSc is a research group on quantum computing, and the main research lines. Well, interestingly, we are in a very particular department, which is computer applications for science and engineering. And very much like this institute, we get funded by companies and public money and equally. So we collaborate a lot with companies. I will explain a little bit about that, because there are many companies that are already interested in quantum technologies. Why? Because of the big hub. Okay, that's natural. And we're gonna also bring interesting points in this discussion when we deal with companies. Okay, so we have two main lines: quantum algorithms and simulation of quantum systems. Okay, quantum algorithms means using quantum technology, whatever it is, to solve problems. And this is on the same line as we use supercomputers and we use any other technology for computing. Okay, so for many users, they don't care about what's the underlying technology for solving a problem. They don't care about if your processor is from one brand or the other, or the architecture is one or the other. They just care about having a good algorithm for solving a good problem. Okay, our bet at the BSc is that the main solutions on the short term will be scientific problems. So we are putting a lot of effort into designing quantum algorithms for practical scientific problems that are of interest. Okay? And these are of interest for communities like yours, but also for people at ICN2, which is like here next door, or people at the University of Barcelona dealing with nuclear physics. These kind of problems we are mostly focusing on. And these are typically problems which have a quantum description. Okay? And I will discuss a little bit why is that. And the second one is important. We don't have good quantum computers now. This is obvious. Okay, we have quantum computers, but they are not very powerful. Most of them can be simulated with a lab. Okay? Then that's a major problem, because we are designing quantum algorithms that cannot be run on the large size. And it's a very important point, because I would say, for instance, one of the main advantages of machine learning is that you can test your heuristics in real hardware, and very powerful hardware. And this is a possibility that in quantum computing we don't have. We are dealing with heuristics as well. We have all these training algorithms on variational circuits, but we cannot train them or try them on the large size, right? Because we are limited by the hardware. So our solution to that problem is to use simulation of quantum systems. But that's a very difficult problem. Okay? And that's the reason we build quantum computers. They are very difficult to simulate. But still, there are many techniques that combine knowledge that we have accumulated over the years on other fields, used on what we call supercomputers or high-performance computers. where we can perform large-scale simulations of quantum mechanics. And this is very useful by itself, because then we can put a line on when quantum computers will be more powerful than classical computers, if you want to discuss this competition. I don't want to do that. But the other is a perfect use case for the simulators. We simulate the quantum circuits that we develop for these algorithms on our own supercomputer. Okay. For the BSc, as a newcomer on this new paradigm, if you want to call it like this, it's important to have an in-house group of people that have some expertise on these technologies. They are used to a completely different battle. It's just how to put hundreds of thousands of computers, regular computers, in a room and connect them through a very powerful network. And then you start talking with the directors and talk about superconducting qubits, dilution refrigerators, photonic devices. They need some in-house knowledge about that, because they are ending up buying all these devices for the future. Okay, so they have to be very aware of this. So these are the main activities. We are a research group, so we publicate papers. Okay, so that's the problem. So I will be more in detail discussing the part of the simulation, which is one of the main activities and our main developments. We use something that has been around in the field of quantum simulation for many years, called tensor networks, but we put them on a supercomputer, and that's our main contribution. Okay. Now, these have been tested so far in small systems, but there is a lot of advantage of putting these structures, these mathematical structures, which are totally classical, into a supercomputer, because this allows us to make simulations of very large quantum systems. I will discuss this in detail, but de facto we end up having a very powerful quantum computer in the simulation. Okay? And this is what we use for the development of quantum algorithms. So we collaborate a lot with external institutions, and the reason is that we are trying to look for applications of all this technology, but we are not experts on any other field, and that's why we need collaborations with experts in different fields and make this conversation and decide, okay, what's your problem? Maybe we have a solution for that, and so on. Okay, so in these directions, we have an internal research group on simulation of fluids using quantum computers, and this may be okay. We have been working in supercomputing centers to simulate fluids, and this is a very hard problem. What new can what's the new thing that we can bring with quantum computers? So we are learning that actually the underlying problem that we are solving here is just systems of partial differential equations. Okay, and we know that quantum computers are potentially very good at solving these problems. So what's the perspective of putting a quantum computer into making a simulation of a fluid? And this is something that for us may not be that relevant. For them, it's very relevant, because on this field they sometimes have the feeling of hitting a wall. They need always the most powerful supercomputer ever in the world in order to run better and better experiments. So they are collaborating with us into trying to just understand what's the potential of quantum computers in order to solve this problem. Again, we are not experts on fluid dynamics. People in my department is, and then that's why we collaborate. Okay, this I will address later, but of course it's important for people dealing with cryptography to be aware of the capabilities of quantum computers, because this is a potential threat for crypto systems. Okay, and then this is probably the most interesting area of our scientific research. We work a lot with companies, and in particular we are studying using catalyzers for particular reactions that are interesting in chemical processes in Repsol, which is a major company in Spain. And then we've been working very actively recently on this nuclear structure problem, which is taking a lot from condensed matter physics and also from quantum computing in order to understand the shape and properties of the nucleus. And this is done with experts on nuclear physics, of course. And then we have an experiment that probably we connect pretty much with what may happen here on detection and anomaly detection in high energy physics experiments. So the idea is that you have an experiment, like a detector running all day long, and then there are a few events among millions and millions of these which are anomalous. And these are the interesting ones, because the new physics may be hidden in this experiment. So how do you detect this? It's a very difficult problem, and you typically need to create a very large operator that will take all this data, process it, and then label which are the anomalous experiments. And then you will take these experiments and make an analysis on this. Okay? Creating this huge operator is very complex, and this is the potential use of quantum technologies in this scenario, because we know data can be codified easily in this experiment. I'm not getting into detail, but then this operator can be either run on a quantum computer or can be decomposed in this mathematical structure that I was mentioning here on TensorFlow. So clearly there's a lot of interest from people in CERN about this technology because, again, they have the feeling that their own technology or the current development of the technology that they are using now will not come up with the pace of development and the requirements in the future. Okay. So there is always a lot of speculation in this field. So we bring with our knowledge of what may happen with our technology in the future, and we compare with what may happen with their technology in the future, and we try to cross lines. And there may be a crossing point where you can say, okay, from this point on, you need to use quantum technologies. Okay. So a follow-up project from this, which we can discuss later, is to use anomaly detection in other scenarios. For instance, in some problems in computer vision or medical imaging. And the idea is the same. You have a collection of images of healthy people, and then you have some images of non-healthy people for whatever problem. And then you try to identify these anomalous situations. The problem is that on the data set for training, sometimes you don't have instances of these anomalies. And this is very interesting. You have to characterize a data set, and then you have to label an image that is not likely to belong to that data set, which is anomalous. And the anomaly may come because there is some strange dot in a particular place of your lungs, which may indicate some problem. Okay? So how do we do that? We typically need to codify the information, which is classical data, into a quantum state. This is an encoding problem, which is very hard by itself. Okay? So once you have your image, you will proceed applying layers. I mean, you know this much better than me, like different layers in a kind of neural network approach for image processing. We can do very similar processing once we have the image or the collection of images codified as a quantum state. And then you define a collection of layers or circuits that can be used for applying these operators. And at the end of the day, you perform some measurement that will tell you a label, a particular label, or a particular indication of a property of the image. Okay? Also, not all quantum ends up in quantum computing. We are also working closely with this company called QSAID that comes from ICFO in quantum random number generators. And this is an interesting field because we run a lot of simulations at the DSC, and these simulations are fed with random numbers. Okay? So typically random numbers that we can generate with a normal computer are non-random numbers, are pseudo-random numbers. But you don't typically care about that because for small amounts of numbers created with these pseudo-random numbers, the distribution is pretty random. The problem is that we run very large simulations, and we always have the question if the randomness will disappear once you have consumed a huge amount of this number. Okay? So we are trying to, and this is also a very active problem in supercomputing centers, to what extent the random numbers can modify the outcome of a simulation if they are not truly random. Okay? So for that, we compare what happens when you run problems or simulations with random numbers and with non-random numbers. And there are many other just derived projects from this interaction. So this is very interesting. So in a nutshell, what we do is to collaborate. This is our basic way of working, because I believe that quantum computing by itself needs to identify all these potential applications, and we haven't found a really good one yet. So we should put a lot of energy into that direction. So let me mention that also we are coordinating this Quantum Spain project. Okay, so after COVID, there was the Spanish initiative on boosting the ecosystem of quantum computing at the national level. So this is a project funded by the ministry with this budget of 22 million, which is coordinated by BSc, and has two main branches. One is for theoretical development, that's the one that we are doing in collaboration with other centers, and the other one is to have a proper quantum hardware installed at BSc. And this goes very much in line with what is happening in other supercomputing centers. To have a big supercomputer, and then next door you have a quantum computer, and you try to understand how to make these things together work in solving problems, or which is better than the other, to understand these new technologies. So this is already happening at BSc. We already have access to a machine which is not installed at the BSc, but it will be installed, because we are installing many things at the same time. We are having Mare Nostrum 5 next month, probably, and then we are removing Mare Nostrum 4, and then we are going to have a quantum computer 1, and then there will be another one in 2025 funded by European money. in the same line as other six European research centers in supercomputing. So on the European level, this is becoming also a very important thing, and the model is very clear. Is have quantum computers alongside supercomputers. So we also work in a very important industrial program in Spain, which is this PUCO project funded by the CVC, and this involves pretty much all the major companies that are interested in quantum technologies from the theoretical point of view. So there are banks, there are like chemical companies, there's energy companies, and they want to know if this is like a big thing for them in the next years. And for that, they set up this project, which is pretty large for a few years, where we define some use cases, and then they get into touch with research centers and simulations that can assess if this is potentially interesting for them. Okay? So we are running simulations for quantum chemical problems, and also classical optimization of industrial processes. So this is very much related to a quantum version of reinforcement learning. Okay. And importantly, we perform a comparison of these two technologies from a different perspective. Not only which computer is more powerful than the other, but on assuming the full amount of resources that you need in order to perform a computation. And the main reason is the following. I may have a very powerful supercomputer, like Marenus 5, but this will take a megawatt of power. Okay? This is very expensive, and it's becoming more and more expensive. Besides the price of the machine itself, it's like 300 million euros. No country in Europe can buy a supercomputer by itself anymore. But on the other side, a quantum computer is not like a laptop, but it's not like a supercomputer either. So making a comparison between these different technologies, if you want to compare them, is not that easy. You need to put into perspective many dimensions. How easy it is to get one, how expensive is the machine, the operation, how long does it take to solve a particular problem. So we are in a position to make all these benchmarks, because we can measure in very detail the consumption of a supercomputer, even at the level of each processor and the memory access and all these things. So this is a very important piece of information that we want to bring also to this discussion. And then we have other European projects. The important one that I want to focus on is this EuroHPC, which is this new generation of quantum computers to be installed at supercomputing centers in Europe. So there are 6 institutions already selected, and BSC is one of these. So there will be a second quantum computer in the next year, let me say, in the BSC. I'm talking too much, right? Because I may, well, let me just, this is what I typically explain to companies. When they come to BSC, we need quantum for our product. And then I typically say, okay, the main application that you may find useful in your problem is that typically everybody is optimizing something. Okay? And optimizing means you have some complex optimization space, and then you have to move around, typically using the gradients. But gradients are difficult to compute. They're expensive, and then sometimes you cannot manage to compute gradients. And then, but I mean, any problem in engineering and science deals with an optimization. The main connection with what quantum computers can do today is not through quantum circuits, I would say, but, and this is a discussion, of course, I understand, but is optimization directly on quantum hardware. Okay? And the main idea is that if you are lucky enough, you can codify directly your optimization problem over a quantum device, over the interaction that happens into the components of this quantum device. And then, at the end of the day, it's not that easy, but it's as easy as turning on the quantum device and let it equilibrate to a particular state. And if you were clever into the codification of this problem, this equilibrium state may be the solution to your problem. So you just need to go and measure. The good thing of this is that we are not computing gradients anymore. So if your optimization problem clearly deals with the computation of gradients because the ill-conditioned objective function, this may be a very interesting approach for optimization. And this has been already tested in many scenarios to any problem that may be described as a network where things are moving in this network. So any logistic problems, network mobility of different things could be like proper stuff like vehicles, goods, or even energy, or, I mean an abstraction of a network in terms of energy or information that is moving around. Okay? But the interesting point is when you go to very large problems, variables, and here again, as a supercomputing center, we have some expertise in what kind of problems can we solve as well using supercomputers. Because sometimes you don't need quantum technology, you just go and in the same way that you don't daily use a supercomputer, but sometimes you may need a supercomputer for that. Okay, and they're having like many different pilot programs, so this is interesting. This is my last introductory slide. I always mention this because everybody knows about this, but just to put things clear, we believe that quantum computers can be a direct threat to cryptography in the future. What's this future? When is that? Okay? And we don't know, and that's a big problem. There are two things that we have to make predictions about the future very carefully in order to know when this will be a problem. Okay? The first one is quantum capabilities. When quantum is going to be powerful in order to make all these cryptographic attacks feasible. And the other one is how good cryptography is going to be developing, classical cryptography, along the years. Because maybe we keep developing classical cryptography, and then having a quantum computer will never be very useful for a cryptographic attack. So actually, to my surprise, I was looking for supercomputers attacking cryptographic keys in order to assess how resistant they are. And there is only one project in the whole Europe, okay, funded publicly at least, that we know about. So it's very difficult to make predictions if we are trying to cross two lines and we don't have information about any of these two lines, okay? Because the only thing that we know is that, of course, companies like IBM are putting their roadmaps and they have a clear picture where they will reach 1 million qubits, which is more or less the limit, the limiting amount of qubits that we need in order to break this cryptography. They are saying around, well, it's called and beyond. Okay? There is not that's not a year, but it's like 2022, 2023, beyond. Okay, that may be 2030, 2040. We don't know. Okay, what I'm trying to say is that we need to know about all these things. If we need to replace cryptography today, that will take years. You have to go to any device on Earth that uses cryptography, which is basically every computer and every phone, and then replace all these cryptographic systems for a new one that is robust against quantum attacks. But that will take years. That will not happen in 1 month. But if that is going to happen, if that takes 5 years, and that is going to happen in 2030, then we need to start replacing everything now. Okay? And we don't have any other candidate. I mean, there have been contests about post-quantum resilient quantum cryptographic methods, and we are not very sure about these yet. I mean, last week or 2 weeks ago, there was a flaw in one of the selected ones from NIST in order to be post-quantum crypto system. So this is an important problem that actually is what triggered the field of quantum computing from the beginning, and I think it should be at least keep in mind in all this discussion. Okay, so I finish here with this. I have a more technical one about the simulation part that I can fit into 5 minutes. Okay. Now I go this. Well, do you have any question? I can.
I have a question in the meantime. So Airbus is using quantum annealing now.
Well, they make this pilot program.
Mm-hmm.
It's not that they are using it.
Okay.
The only company I know they bought a proper quantum computer was Volkswagen. And I don't know why. They probably had money and a research team, and also Lockheed Martin, but that's a different story. And they were running like massively like experiments for optimization in their lab. So yeah. So this will address the problem from the classical point of view, how to simulate a quantum computer. Okay? And I'm going to discuss a little bit techniques and things which maybe I'd like these to motivate things that we can do today. I mean, if we want to set up a project and collaborate and focus on particular applications, then there are some limits of how far we can get, but there are many things that we can do that are beyond what is typically believed to be able with a normal laptop. This is a picture of the supercomputer at the DSC. So this is Milestone 4, which is very old. It's almost burned out, and we are going to have the new one next month, as I was saying, Milestone 5, which is much larger than this one. It doesn't fit in this chapel. It's already installed in a different room, which already tells you about the situation in supercomputing. We are no longer in these golden years of Moore's law. if you want a more powerful supercomputer, you have to pay much more money and then go to a much larger system. I mean, Mare Nostrum 1, 2, 3, 4 were already fitting always in this room. And Mare Nostrum 5 doesn't already fit. I don't have any idea what Mare Nostrum 6 may look like. But they may consume, I mean, as much power as a full city. So this is an interesting discussion that has to be also placed into the table. What are the alternatives to quantum computers in the future? Not the other way around. Okay. So I already went through this. So Matías was showing an interesting experiment that was run 2019 with this device by Google, and they were claiming quantum supremacy, which is a very nasty word. We use now quantum advantage. Okay? The idea is that to run an experiment, whatever it is, that can only be computed with a quantum computer. Cannot be computed with the most powerful supercomputer on Earth. Okay? They were suggesting, their proposal was to compute the distribution of the outcomes of a random quantum circuit. So you take this circuit, you put random couplings between a very modest amount of qubits, which was 53, if I'm not wrong, and then you compute some properties of the distribution of the outcomes of the circuit, which we can bound theoretically and know if this system is actually behaving as a quantum device or not. But there is a region, according to their claims, for which if you make proper quantum circuit of a given depth, the outcome is quantum, but the outcome is very hard to compute by a supercomputer. Okay? So there is like a very small region where actually using a quantum device is very useful. Of course, the applications of the problems are nothing very useful, but from the theoretical point of view or academic point of view, it was a very dramatic moment, okay? Which took everybody upward, I would say. We didn't expect this, and the main reason, the main learning from this is that at this moment, we were not prepared to simulate large quantum circuits in a supercomputer. Nobody cared about this product. We always care about simulating quantum circuits in small computers, but going and make a very large program that will make a simulation of a quantum computer is a very complex task. Programming in parallel this simulation is not an easy thing. It took almost 2 years to some group in a supercomputing center to replicate these results. So there is no longer quantum advantage because actually this can be done in a supercomputer now. And a few months later, somebody did the same calculation by some clever theoretical analysis into a laptop. Okay? So every time there is somebody announcing quantum advantage, and this happened recently again with IBM, the community uses this result to trigger some discussion and learn a lot about new techniques in order to make these simulations. Okay? So it's a very interesting moment to be in a supercomputing center observing all these, I would say, battles. But at the end of the day, we actually are learning a lot about making simulations, and we take advantage of that because then we use these simulators in order to test our quantum algorithms. Okay? And then from there, you can assess also which are the best quantum computers. So how do we do these simulations? So we use something called tensor networks. And tensor networks are everywhere for many years. We are not discovering anything new, but we are putting them into use in quantum simulation. So these are mathematical structures that have been discovered many different times in many different fields. And the idea is very simple. We have these objects, these mathematical objects, which are tensors that are an extension of matrices. So they are not much different than a hyperdimensional matrix. And they have connections, which basically, if you think about matrix multiplication, is the common index that you use in order to make this multiplication. Of course, you can generalize this to any amount of tensors, any amount of connections. And then at the end of the day, you have a small tensor network, or you can end up having cube tensor networks. Okay? And then you have to make operations over this tensor network and bring these operations in contact with what happens in a quantum circuit. There has to be a one-to-one translation. So there are interesting properties of these tensor networks. Okay? So first of all, if I give you a quantum circuit, I can write easily this structure without no overhead. And then I can perform optimization of this structure of this tensor network on supercomputers because many of the operations that will deal with these tensor networks may happen in parallel. And this is what I like. As a programmer in a supercomputer, I can discuss what happens here and what happens here independently. At some moment, I will have to agree on these results, but this can be done very easily in a parallel system. If I have a one-to-one correspondence, and I am saying always that simulating a quantum circuit is very expensive, the worst case scenario is going to be expensive at all. There is no free lunch. Okay? But tensor networks have a very magical trick where we can make approximations in a very clever way. And then we relax these exponential cost into polynomial cost. How good this approximation is, we don't know. We have to test and do experiments. Okay? But at least the possibility is there. And also, a very nice connection between what happens here and then some physical properties of the physical system that we'll have to deal with this simulation. For instance, if I have a quantum circuit that shows a very large amount of entanglement, I know that my approximation here will be very bad. Okay, so I have a physical inspiration for it. So, as I was saying, obtaining this structure is trivial. Then we have to compute something which is what we call the contraction, which means basically to take any open index in this structure and make the product. Okay? And once I make all these products, I end up with a single number that will be equivalent to the outcome of the quantum circuit, okay? Which is what I'm looking for. Then the problem is that actually this contraction operation is going to be very expensive. I'm going to put a lot of effort computationally into solving this contraction. But then I can use this equivalent to compute easily quantum magnitudes. And then if I go to a supercomputer, I just need to program tasks that will do most of this in parallel. Okay? This is what actually my group is doing. And we are programming this. We are members of a small group of people doing this because there are not so many quantum computing groups in supercomputing centers. So this is a very interesting point. So once we have, so these two things are totally equivalent from a mathematical point of view, the quantum circuit and this huge tensor network. So I need to perform operations among all these tensors in order to end up with the same distribution of numbers that I would get from the quantum circuit. And for doing that, I need to first set up the tensor network, which is easy, and then compute and optimize the contraction path. So basically, the result is going to be the same, whatever the ordering of the operations that I do in parallel. But of course, some of these operations, the ordering of these operations may end up in a more efficient simulation, okay? Because there will be intermediate structures that can grow very, very large on these operations. And this is the thing that I try to minimize. This is a classical minimization that I have to perform, and it's very expensive. We need new methods for that. And we've been learning that thanks to this kind of competition with this other, like with the real quantum circuit evolution, okay? So we minimize this intermediate representation of tensors because these may be so large that they don't fit in the memory of the full supercomputer. Okay? And then at the end of the day, I will, once I know which is the best ordering to perform all these operations in parallel, I go and actually perform these operations. Okay? So this will happen just taking the full memory of the supercomputer, and then at the end of the day, I perform some sampling in order to get the outcomes of the random circuit. So it's quite an involved process, but most of these things are algebraic operations that we know to do very well in a supercomputer. So, and the main key thing here is that we need new heuristics. Computing exactly the contraction path is very expensive. But on the other hand, we run then this contraction in parallel, which is very, very, very nice. We need something called slicing. And the slicing idea is the following. Sometimes these tensors will be so big that we need to fit them into different nodes, different parts of the supercomputer. Okay, they don't fit in a single node because the memory is too much. But still, we can perform operations in parallel, even though the tensor is not on the same node, located on the same node. So this speeds a lot what we can do, and this is probably what we have learned more about in the last years, thanks to this kind of discussion with the quantum technology. So we are not using at this moment approximation, but this is something that will reduce the size of these tensors and increase the capability of the simulation. And more importantly, Mare Nostrum 4 that I showed before was set up in 2017, and it didn't have any GPU. At that moment, supercomputers didn't consider GPUs as a useful tool for speeding up or boosting operations. In 6 years, everything has changed dramatically. Any modern supercomputer will have thousands of GPUs. The good thing is that actually any operation involving tensor manipulation gets boosted by using GPUs. So next month we are going to have like 5,000 new ones, and we are going to get there and use them. That's crazy, okay? So the thing is that with all of this together, this is a very low level work or development. But we are also putting a lot of effort into bring this to people in the group, in our own group, but other groups that may use these tools easily without knowing about slicing, tensors, or anything. They just want to perform a simulation of a quantum circuit and get the outcome. Okay? So this is a tool that we are preparing in order to bring all these capabilities, supercomputing capabilities, to other groups. And just to finish, I was mentioning, we are not the only ones. We have made several versions of this library. This is the first one, but the new one is developed in this language called Julia, which is very powerful for supercomputers now. And then, of course, we want to put that in practice with our own algorithms in these different fields, machine learning and fluid dynamics. And then the other thing is that we are using these tensor networks also in science, in physics in particular, without the connection with quantum circuits. Tensor networks by themselves are a research field very, very mature and very interesting, that may be used for solving problems which are very hard otherwise. Okay, so this is a side effect of every development we've been doing, and on which I was working a lot many years ago. So I think I finished with that. Thanks a lot. That's the last one, yeah. But anyway, I'm done.
Thank you, Artur. We still have
Fernando for this amazing introduction. So I am Matías, yes, I am a physicist. I'm very happy to see very new faces and some faces that, well, I know very well. So yeah, I will give an introductory talk now for about half an hour on first quantum information, then I will tell a bit about my PhD, which is on quantum machine learning, and then I will try to devise some research lines here in the CVC. But this talk, I want you to have it very clear. It's not a physics class, so I would like to transmit some ideas so you to grasp the paradigm now, but don't feel bad if you don't understand everything of what I said, okay? You can ask me questions later. I will stay here for at least 2 years. So let's begin, okay? And also, today we will have this opportunity that we said many, many times on doing this hands-on tutorial, okay? So before beginning the presentation, I like each time I join a new institute or place to say, well, which is my trajectory, which unfortunately each time is bigger. So I come from Argentina, and just in case you don't know Argentina very well, we won the World Cup last year. And I studied physics there, and then I joined the JIC, the Quantum Information Theory Group, around 5 years ago to do my PhD under supervision of John García that we have today. And I finished this PhD last June, and I reached out to Fernando, and here I am in the Computer Vision Center. Okay, so I would like now to provide you with some very, very basic concepts of what we study in quantum information, okay? So, the idea that we have in mind is that information is physical, and there is a very important theory in physics, that is quantum mechanics and quantum theory, that describes nature, okay? And usually we say, okay, we have a system of study. This can be, say, electrons, light, that is very important for vision, right? Or even the universe is a physical theory. And, well, this theory predicts very, very counterintuitive phenomena that is not the phenomena that we experience in our classical world, okay? So there is some kind of transition between the quantum world and the classical world that we really don't understand very well, and it's the current research topic of research. But I would like you to get this notation. So this thing, we call it the quantum state of a system, and if you Google quantum physics or quantum state or quantum computing or whatever, you will see this very often. Okay? So the first difference between the classical world and the quantum world, let's consider a very, very, like the simplest system that we can imagine, is a system of 2 levels that we call it the quantum bit, okay? we know that the classical bits that we use to process information, classical information, they can have two states, which is the 0 or 1. In quantum physics, these qubits can be in a superposition of 0 and 1. Okay? This is the so-called block sphere that shows all possible states of a qubit. Okay? And once we have prepared this quantum state, we would like to extract classical information out of this. And for this, we need to ask the qubit a question. This is a quantum measurement, okay? And this plays a very important role in the quantum theory and is also very subtle, okay? The most important thing is that each time you ask a question to a quantum state, it retrieves a bit and the result is probabilistic. Okay, so what I want you to get out of the previous slide is that quantum bits are very different, or can be very different than classical bits. They can live in a quantum superposition, and to get information out of them, we need to measure. Okay, so we can extend, so quantum theory goes beyond this quantum superposition phenomena, and we can think of the state of two qubits. Okay, we have two-level systems. And here, a very, very important phenomena appears, which falls under the category of quantum correlations. And to showcase this, I wanted to present you this simple game that people devised to showcase the quantum correlations, which is called the CHSH game, in which Charlie is a referee. Okay, so we have three players. We have Charlie here, Alice, and Bob. Okay, and Alice and Bob, they can be very far away from each other. So the game consists in Charlie sending random bits, classical bits, of information. They can be 0 and 1 to Alice and to Bob. Then Alice and Bob each needs to retrieve an answer to Charlie via a classical bit. Alice sends A and Bob sends B. Okay? And the score of the game is whether the sum modulo 2 of the answers of Alice and Bob equals the product of X and Y, which were the questions, if you want, that Charlie sent to each. Okay? So, using the best classical strategy to play this game, one can find that the success rate, which is on average how well you do, is about 3/4. Okay? Whereas if you use quantum correlations, you can beat this. How do you beat this? Well, by using quantum entanglement and giving Alice and Bob a shared quantum state, which is of this form. Fine. So, what I want you to get out of the previous slide is that quantum physics allows for a bigger class of correlations, which are known as quantum correlations, and in some particular tasks, if we use them cleverly, they offer a quantum advantage. However, manipulating, controlling, and even storing quantum states is hard. Okay? So we need to be careful with this. Okay. So the paradigm, more or less, is exactly that one. We have the fuel, which consists on quantum effects, and then we have quantum technologies, which are very promising. They are very promising because they might deliver a quantum advantage, and they might allow us to do things that we cannot do today. We have many examples of the promises that we can discuss in a later talk. Okay? So, what I would like to show now is which is more or less the state of the art on quantum computing, quantum technologies. So, since the last 30 years, more or less, 80 plus 30 is 2020, yes, there was a boom in the number of publications on quantum computing per year, okay? And nowadays we are in the stage of having the DeLorean, which is the car of Back to the Future, right? But not working perfectly fine, okay? Still, we can use the DeLorean chassis, I don't know if the English is chassis, the parts of the car that we have built up to now, to deliver quantum advantage for a very particular task that is relevant only in academia, okay? This is already very impressive, because in the experiment, we can build a quantum computer, which doesn't work super well, but still allow us to perform tasks that a classical computer would never be able to do. Okay, so with this, I finished my introduction to quantum physics, quantum information, and more or less the state of the art of quantum technologies. And now I would like to spend 10, 15 minutes, let's see, discussing what are the projects that I have been working with the quantum information theory group at Autónoma during my PhD. Okay, so my PhD is entitled, my PhD is entitled Decision Making in Quantum Environments, and I defined it last June, right? This is the cover of my thesis, and this is the logo of the quantum information theory group. And in my thesis, I study 3 paradigmatic problems in quantum technologies, and I provide a framework for machine learning, decision-making algorithms to work on such problems. So the first problem I study is about long-distance quantum communication, where we want to transmit information from one party to another party using quantum states. So this reduces to a fundamental problem that we have in quantum information that is known as the quantum state discrimination problem. We have 2 possible quantum states that our quantum state can be. And we are giving a quantum state, and we would like to label it. It's either psi0 or psi1, okay? If you want, this is a classification problem, and the model that best tells us which is that quantum state is often very hard to find. So, in this project, what we focus is on sending a classical bit of information from one party to another, and to this end, we use lasers, okay? So we encode the value of a classical bit into some property of the laser, and then the laser pulse travels along, for example, the atmosphere by a very long distance. At the receiver part, say this is Alice and this is Bob, Bob will need to decode such classical bit of information. So let's assume that we send a classical bit from a satellite, and what arrives in the satellite in ground there is very, very, very weak pulse of light. Okay, it gets very attenuated. So quantum effects here become very relevant. So all in all, to get out this information, as I mentioned in the qubit case, we need to ask some property to that quantum state. We need to implement some quantum measurement. So we can quantify how well a quantum measurement does, and this is the success probability, and it turns out that the success probability is bounded by quantum physics, and I don't want to enter too much in details. However, we can theoretically find which is the best apparatus that distinguish between the 2 signals. This is theoretically, but when we want to implement it in the lab, well, we have some problems. And experimentalists have come up with a hint of how it is the mechanism to decode that information, what you should do to the incoming signals. And we have some intuition on how it works. What we would like to do is to generalize this intuition to cases where we don't have this intuition. Okay? So this project, as I said, is about decoding the information using this apparatus. But in practice, this apparatus it's very hard to be used, and it's even harder to use it if you don't control perfectly the experiment. So what we did is to cast this problem as a reinforcement learning problem, and I know that many people here work on reinforcement learning and self-driving cars, which I find amazing. Okay, we trained this discrimination problem in terms of reinforcement learning using a blind agent, and we can see the training curves, the learning curves, etc. And we can see that it adapts to a variety of scenarios where the agent ignores how is the transmission channel. Fine. So this is the end of the first project, okay? If you resonate with this, let me know afterwards. There are many open problems that we have. I think it's maybe better if I move this here, if you don't mind. One of the problems that we have is how to implement state-of-the-art tools like deep reinforcement learning to this particular setting of quantum communications, okay? So, if you want, this is a classical adaptation of reinforcement learning to a quantum experiment. Fine. So next I will drink some water and then I go on, if you don't mind. Okay, the next project I have been working on is related to quantum computing and to quantum computing nowadays. Fine. So this is the circuit design problem, and this is a picture of a superconducting quantum computer that I think is the Google one, but I might be incorrect. Okay, so in this project, what we care is about these quantum computers that people have built to experimentally demonstrate quantum advantage 2 years ago. And we know that they are very hard to control and they are very noisy, and they cannot be very big. However, we can actually prepare some genuinely quantum state. We can observe these quantum correlations, we can prepare a quantum superposition, and this is already very interesting. Whether we can use these machines to provide a quantum advantage for a task which is relevant for, say, computer vision, industry, etc. It's an open question. We are doing a lot of effort to try to tackle this. Okay, so this whole paradigm of near-term quantum computing falls, and some of it is encapsulated by the concept of quantum neural networks or variational quantum algorithms. The idea is that people have made an analogy between quantum circuits and neural networks. This is a quantum circuit, okay? So a quantum circuit has, I have shown you the case of 1 qubit and 2 qubits. Here we have 3 qubits, and imagine that the quantum circuit that delivered this so-called quantum advantage has 53 qubits, okay? So here we have a quantum circuit, and the idea is that you read the quantum circuit from left to right, and you can apply transformations, which are called quantum gates, and each transformation is parameterized by some parameter, and the analogy is that each parameter might be the weight of a neural network, okay? So then you use this quantum circuit to measure something, some cost function, okay? The quantum circuit is known as an ansatz. Then you quantify how well a quantum circuit does by defining a cost function that encodes the problem that you want to solve. And then you would like to change these parameters, the weights of the quantum circuit, to minimize such cost. As I said, measuring in quantum mechanics is something subtle, and here we don't have in the experiment, say, autograd or TensorFlow or PyTorch that gives us the value of the cost function, but we need to estimate it through repetitions of the experiment. Okay? So even more, I said that we need to tweak the parameters. And to this end, we can use the classical optimizer, and you do, for instance, gradient descent. But to do this, we actually need to get the derivative of the quantum circuit with respect to each parameter. It turns out that you can measure experimentally this gradient of the quantum circuit. Okay, and with all this apparatus of estimating the cost function, optimizing the quantum circuit by estimating the gradients and using a classical optimizer, you can make the machine roll. But one or many problems arise, and to mention some, first of all, if I have a problem, say I want to encode the NIST classification problem into this setting of quantum computing, it is not very obvious which is the layout, which is the quantum circuit that we would need to use for this particular problem. We don't have, in general, an intuition. For some problems, we do. And second, this is a very important no-go result, that for some of these circuits, we have a quantum effect known as the Barren plateau, which says that this gradient is exponentially vanishing. So it will be very, very small, and the optimization procedure, it will not work. So currently, there are many, many efforts in studying whether some quantum architectures, some quantum circuits exhibit a Barren plateau or not. Okay? So some do, and some others don't. Okay? Fine. So what this project is about is trying to find a classical algorithm, and we developed it, it's called VANS, that not only modifies the parameters of the quantum circuit, the rotations, but also tries to optimize the structure of the circuit. Say this might be important because, as I said, some quantum circuits exhibit a Barren plateau and cannot be trained, and some others, well, they don't. Okay? So we actually need methods, new methods, to find new structures of quantum circuits. Okay. So we proposed an algorithm which is called variable ansatz algorithm, and we stole the name of VANS, which is Shu brand. And more or less the algorithm works like this. If you want to find more information, you can ask me or anything. But the idea is to grow the quantum circuit by randomly appending gates, but then try to compress it, because training a very large quantum circuit has two problems. First, the landscape becomes very, very challenging. And secondly, if you want to experimentally implement such quantum circuit, noise will accumulate and it will be useless. Okay? So we randomly insert quantum gates into the circuit, we train, and then we try to compress it using some quantum informed simplification rules. Okay? And we have some acceptance or rejection criteria, and we let the algorithm roll. And well, we ran a lot of experiments, but what we see, what I wanted to show you here is that for a very important cost function that we quantum physicists care about, our algorithm VANS can adapt to a wide variety of noise scenarios and noisy levels, which is very important here because our devices now are quite noisy. Okay, so there are many open problems here. One of the research lines and continuations of this project that I might devise is that, okay, we need clever insertion rules, like the way you append quantum gates to this circuit layout. And to this end, I think that there are many methods developed by the classical machine learning community, and many people here in the computer vision center, they are experts in trying to encapsulate such knowledge into some architectures of deep learning, say, I don't know, graph neural networks, etc. This can pretty well be understood as a graph optimization problem. Okay, so with this, I would like to comment very briefly on a quantum sensing problem that we have been tackling recently, where here this is a completely different problem, yet very focused on an experimentally on an experiment that people do nowadays, which consists on measuring a system continuously. Instead of taking a photo of the system, you are watching it continuously, and this has a lot of consequences in quantum physics. One of such consequences is that the system will be described by a very, very complex equation of motion, and I will not enter there, but we get a signal, a continuous signal, okay? And from this signal, we would like to infer properties of the quantum state. And in this project, we care about hypothesis testing, like trying to distinguish between two possible dynamics of the quantum system. Say that the dynamics are affected by two values that the environment might have. For example, an electric field that might be there or not. And then we care about estimating parameters, giving the value of some parameter that is hidden there in the dynamics. For example, the intensity of such electric field, which is in the surroundings of the quantum system that we are monitoring. Okay, so first we care about the hypothesis testing problem, and I know that many here are aware of such problem. Say, for instance, that I throw a coin many times, and I would like to tell the bias of such coin. You can encapsulate your knowledge up to the end trial with a log likelihood ratio. And then you can devise a test that after n samples, then you vote for the most likely hypothesis. And this, we like to call it deterministic test, because you need to measure n times, n samples, and then bet. But people from the statistical community know pretty well that this is not the optimal thing to do. And we brought into the field of quantum continuously monitoring what is known as the sequential probability ratio test, which sequentially tests the value of such likelihood. And after some time, if you hit some boundary, then you bet for some hypothesis. But you have the freedom to say, okay, no, I don't have enough information. Okay? So here in sequential strategies, we care about such distribution of the stopping time and when do you hit the boundary. And importantly, all this machinery, we have applied it to the system that I was telling you about, which is a quantum system that you are continuously extracting information out of it. Okay? So this dynamics is very complicated, but the reason I wrote it is not to say that quantum physics is complicated, because, well, we can study it, and it turns that, well, with a lot of work, you can understand a bit. But here in this equation, it naturally appears a Wiener noise, which is, as far as I understand, very relevant for diffusion models and generative models that people in the computer vision center actually cares about, as far as I understand. Okay, so there are platforms there like atomic sensors and optomechanical cavities, and the idea is that, okay, I get a stream of data, and I would like to say, okay, it was generated by hypothesis 0 or hypothesis 1, and look, they are very noisy. But, okay, if you compare how much time you need to wait until to accomplish some error of the discrimination problem, then we see that the sequential strategy does much better than the deterministic one. And this is very fine, and we released a paper a couple of months ago. And now what I am really caring about is what we are studying now is the parameter estimation problem, where from this stream of data, you would like to infer the value of, say, that electric field. And we have some preliminary results in which you use a recurrent module that simulates the quantum dynamics, and it is useful to predict the dynamics of external signals, to provide a model similar to what this line of research does. I don't know if someone knows SINDI, which is sparse identification of nonlinear dynamics, and it comes from the classical community. And okay, well, I am working on this, and there is a strong possibility to find intersections between diffusion models and this physical platform. Okay, so finally, I would spend 2 minutes telling about quantum machine learning and my impression. So, my personal impression, but I think that many share this with me, is that the field is a baby. It was born not so long ago. And we are researchers, we are scientists, and we need to be very careful in how treating this field. There are many hypes which are encapsulated by, well, I don't want to blame anyone, but we need to balance the hype and the hope, okay? And I do think that there is hope, and of course we have empirical evidence, experimental evidence of a quantum advantage. This is on the one hand. On the other hand, the technology reached a stage in which you cannot get rid of quantum physics. And I think that, well, the best analogy I can think about is when, on the first project, that you have this signal which is very attenuated, but it carries on it classical information that you need to decode. And for this, you need to implement the quantum measurement, okay? This is an analogy, but there might be others, okay? And finally, my impression is that we actually need to change a bit our minds and be very open. And this talks for the quantum information computing community and also the machine learning community. And I think it's very healthy that all of a sudden there is a research line in an institute, in Machine Learning Institute and Computer Vision Institute of quantum machine learning. And in this regard, I think that, well, I personally don't like frontiers, but this chart that Fernando showed in his presentation says that, okay, we have classical algorithms, we have quantum algorithms, we have quantum data which exhibits quantum correlations and quantum superposition, and then we have classical data which doesn't. And then we can say, okay, I will apply my quantum computer for this stuff, for this other. Nowadays, I think that each of these sub-areas need to make some symbiosis with the other. And well, we were discussing with Fernando, and it turns out that so what I like is to think of a classical for quantum for classical. And I think it's very relevant here. And well, I was very surprised because I don't know the English for the CQC, but it turns out that this is the name of a very popular TV program in Argentina. And what I think is that it's actually worth it to put effort in helping the classical, in helping the quantum algorithms to tackle classical problems, and how can you help them? Well, with classical methods, okay? And that's why CQC. And with this, I am ending 32 minutes. And I would like to invite you, if you feel that this might be interesting, maybe not, it's okay, to the hands-on tutorial that we have prepared. It will be very basic, you shouldn't be afraid. But on the first part, I will introduce the notion of a qubit, of a quantum measurement, etc. But this will be oriented to provide well, whoever wants to join with some tools to actually implement this by programming. Okay, and there is a library. Well, there are many libraries. I will show. I will do like a map of many of them, and then we will use one known as Penny Lane. And well, then we will do something a bit more serious, which consists on training this quantum neural network to do something. And well, I thought that maybe there was a problem that might be relevant, which is image generation using quantum circuits. And well, yesterday I was thinking, okay, let's see what to implement. And well, this is something that, well, I thought that if some are interested in, we can collaborate further. And I managed to make a quantum circuit to print like CVC, QML, which are like the letters of the group. And that's it. And well, of course, you know that these are very, very, very hard times. And I am from Argentina. I listen to the news in Argentina every day. It turns out that there will be general elections in Argentina next Sunday. And it's quite likely, I hope it doesn't happen, that a fascist will come to power by popular election. This is very weird, but it might happen. So, well, I would like to say stop fascism. And with this, if you want to access the slides, there's the QR. And well, I think that now, Artur.
Yes, thank you. I didn't know that we had a logo already for the
Okay.
Okay, good. Thank you very much. Artur from the VSC and Qilimanjaro, and